Hey everyone, this second video on our lectures looking at D-block chemistry is going to be a slightly shorter one, and we're going to be looking at some of the trends such as atomic radius and ionization energy, both across a period and down a group. Let's start by looking at the atomic radii, and we're going to be doing this looking at the first row of the transition metals and going across this, because it doesn't quite follow the general trend we'd expect from what we've learnt before. So usually as we go across a period, we see that as we go across, the effective nuclear charge increases because there's more protons in the nucleus, but the electrons aren't effectively shielded. And this increase in effective nuclear charge means that the atomic radius decreases because the outer electrons are more tightly held, they're sort of pulled in. However, this isn't so true, and the trend isn't so straightforward in the D block or the transition metals. And in fact, the sizes across the period don't change so much, and that's why we can get a lot of interest in intermetallic chemistry done with the transition metals, because if you remember back to the solid structures lecture, we had a type of alloy which was substitutional, where you have a metal crystal structure and one metal atom is replaced with another. That's super possible with these metals because they can be really similar sizes, so it can just be take one out, drop one in. The lattice doesn't change too dramatically. But let's look a bit closer at this first row and see the trends. So at first, it does happen how we expect it to. So going from scandium to chromium, it decreases as the effective nuclear charge increases. Then we've got manganese here, which is a bit of a bump, quite an anomaly. Then it levels out and it's very similar, and then it goes up a bit towards the end. Now, I'll make a note here that working out atomic radii isn't so clear cut. There isn't such a definition. It can be done numerous ways. One of them is looking at the bond length between, say, well, let's look at manganese in this example then, manganese-manganese bond, and dividing it by 2 to get the atomic radius. But there are many other ways, and because there are quite a few ways of doing it, these graphs quite often looks different. So I've taken this graph from the textbook, which shows manganese as being quite an anomaly. If you just Google transition metal atomic radii, quite a lot of the graphs won't have manganese so high up, and it is actually just quite similar to chromium and iron, like all the others. So also the textbook doesn't give a good reason for manganese having this anomaly. So take it with a grain of salt and realize that this general trend of it starting high, going down, and then coming back up, this is for sure a thing, and we've got reasons for that. We've also got reasons for why it doesn't continue going straight down. This manganese anomaly, I take it with a grain of salt and kind of ignore it. So what happens at first? It happens exactly how we'd expect. The effective nuclear charge increases, so the radii decrease. But then what happens is we start pairing up d electrons. And the d electrons don't like to be paired up so much. There are actually quite a lot of electron-electron repulsions as they get paired up. And around this period, we can see from chromium, if we ignore manganese anyway, all the way over to copper, they're very much the same size. And this is because as the effective nuclear, the charge from the effective nuclear charge is increasing, but in terms of atomic radius, this is offset by the fact that the electrons are wanting to repel. So even though the effective nuclear charge is higher, they don't want to be pulled further in because they're going to be brought closer to each other, which they really don't want. So here, the balance between effective nuclear charge increasing and electron-electron repulsion increasing is balancing out. And then as we get towards the end with copper and zinc, then it's the electron-electron repulsions that are winning out and the size starts to get larger again. But as I said, in this section, like everything's very much a similar size. So you can make alloys with these really easily. Like going back to my PhD again as an example, I was also looking at making alloys of the metals as catalysts for decomposing ammonia. And these three, iron, cobalt and nickel, I made a lot of alloys from just because it's so easy, you can just substitute them, and this is mainly due to the fact they're pretty much exactly the same size. We've also got weird things going on with the atomic radius going down each of the triads. So for the case of this, again, I've taken off this bottom line of the periodic table because yeah, they're the heavy ones that don't really exist. So if you look at the triads, yeah, it doesn't happen like it should. So usually as we go down a group, the atomic radius increases because the valence shell is much further out, it's much larger, and it should increase smoothly. But in this case, it doesn't. As we go from the first to the second row, it does increase, but then from the second to the third, we can see in a lot of cases it's the same or just 1 picometer different. And I would say at this moment again to reiterate how in the book they say that manganese is really big, but I'm doubtful of this. I'm putting these in because they're from the book, and that's the text. It's what you'll be following. But be aware that this manganese number I'm doubtful of because a lot of sources on the internet don't have it. I've got a link down here that I'll put in the description of the video to one of the online resources that's really good for a lot of topics to learn from. Actually, they've got some graphs which are much smoother and don't have manganese having this crazy value. They've got it more, so 128. So going on from that, from the first row to the second row, we do see it getting bigger because the outer electrons are from the 3d orbital into the 4d, which is further out. But from the 4d to the 5d, we see that there is pretty much the same size. Now the reason for this is highlighted by the green bit here. So where the lanthanide elements start, the F block. And this means that the F orbitals are filled before the 5d orbitals. But something very important to know about these 4f orbitals is that they're very poorly shielded. So that means the effective nuclear charge felt by these is absolutely enormous. And it's also referred to as the lanthanide contraction. So what happens is, the same as effective nuclear charge going across a period, I guess. There are more protons going into the nucleus. The electrons being added aren't doing anything to shield that effect. So the nuclear charge is stronger and it gets pulled closer. However, here it's so large that even though the outer electrons are in a 5d shell rather than 4d, they're the same size. Because going down a group, we've added tens more protons to the nucleus, but these 4f electrons are doing absolutely nothing to shield it. So you get this hugely high effective nuclear charge, which is big enough to bring a 5d shell to the same radius as a 4d shell. Finally, we got the trends in the ionization energies across the D block. And remember I said the chemistry of the D block is dominated by cations, therefore the ionization energy is going to have a big effect. So in this graph, we've got the first, second and third ionization energy values for the first row D block metals. So at first, the first ionization energy follows the trend we generally expect. I mean, it increases from left to right, and this is because of the effective nuclear charge increasing. So the valence electron that's going to get removed is slightly higher held as we go across the slightly tighter held as we go across the first row. So it takes slightly more energy to remove. Also generally follows this trend on the second ionization energy as well. So as we go from left to right, they're generally increasing, but it isn't quite so smooth. And there are some small anomalies that you can see I've highlighted here. So from chromium to manganese and from copper to zinc. And in this case, why these are slightly higher than the one after them is because of the half or the completely filled orbitals. So at this point, if we remember back to the first video, actually I can just write it down here, the electronic structure of chromium will then be 3d5 4s1, and for copper it's 3d10 4s1. So the first ionization energy will just be removing that 4s1 electron in either chromium or copper, and then we're left with either a half-filled orbital or a completely filled orbital. And if you remember, these half and completely filled orbitals are much stronger than usual, so it's slightly harder to ionize an electron from those, and that's why we see chromium and copper being slightly higher than expected and making this trend a little funny. And then finally, when we get to the third ionization energy, here's where things aren't smooth, and there's this really big decrease from manganese to iron. And the reasoning for this is electron pairs, an electron pair. Now if we look at the electronic structure of iron at this point, so at this point we've lost two electrons, so we're actually looking at iron 2+. This will have the electronic configuration of 3d6, and because there are only 5d orbitals, this 6th electron, which is going to be the next one to be removed, is paired up with something. Therefore, the electron-electron repulsion from this electron pairing makes it slightly easier to remove, and that's why we've got this decrease going from manganese to iron. And this will be important in the next lecture as well, because we're going to be looking at oxidation states in the next lecture. And obviously oxidation states are really closely tied to ionization energy because they're losing electrons. So we'll come back to this in the next video also.